Alright guys, last day of lecture, and then tomorrow I'll give you like a quiz assignment or something on Google Classroom to just kind of see how we did. As always, post comments, questions, anything like that, and I would be more than happy to help. So, we're going to start with the heat of formation of benzene. My answers, as you can see, are right there, so I got an answer of 49 kilojoules, and I was hoping that a piece of paper maybe would work better. I don't really know, but I always start by writing the whole equation out, as you can see on the very top, and then I like to write out the equation that I'm given or need to use. So in this case, it was delta H equals the sum of the heats of formation of products minus the heats of formations of the reactants. And before I put in numbers, I do like to solve for what the like X is, or what it is that you're looking for. So because we were looking for the heat of formation of benzene, we're going to be trying to solve for the delta HF C6H6. So you can see that I put in the heat of formation of the reactant, or excuse me, the enthalpy for the reaction will equal your products minus your reactants. So in this case, it's the heat of formation of H2O plus the heat of formation of CO2 multiplied by their coefficients, so 3 and 6. And you have to put those in parentheses because you need to solve for that first, and then you subtract it from your reactants, which were O2, so again in its standard state, which can be ignored, and benzene, which is what we're trying to solve for. So once you get all of those different parts there, then you can solve for the heat of formation of benzene, which is done by basically adding delta HF C6H6 to one side and then subtracting the H of the reaction. So you get delta HF C6H6 will equal 6 times the heat of formation of carbon dioxide plus 3 times the heat of formation of water minus the delta H of that whole reaction. So then all you have to do is plug in your numbers and calculate them, and hopefully you get the same answer that I did, which was 49 kilojoules. And then when you're trying to solve for the delta H of the reaction, the reverse reaction, and taking out the 15 halves coefficient, so multiplying all the coefficients by 2 to get that 15 halves to become 15, a total of 15, so that 2 gets out of the denominator. You can see that I rewrote again that equation on the bottom, so 12 CO2 plus 6 H2O yields 2 benzenes plus 15 oxygens. Because it's the reverse reaction, you need to make your sign the opposite. So because in the beginning it was negative 3,267.4, it becomes positive 3,267.4. And because we multiplied all the coefficients by 2, then I have to multiply that delta H by 2, giving me a total of positive 6,534.8 kilojoules. So I understand that that was probably more complicated than the other ones that we've done, and you may have a lot of questions about it. There will be more practice on the homework tomorrow, and if you need more help or more practice, I'll post some extra videos or tutorials, things like that, on our Google Classroom. So just be looking for that. All right, we're going to talk about bond enthalpy, which is this kind of like last section. So it's a basic property of molecules that when they're involved in reaction will determine the sign and magnitude of delta H. So in reactions, as we know, bonds have to be broken and then reformed. And the energy that is given off or absorbed when those bonds are broken and reformed will give us the total energy of that reaction. So using bond enthalpies, you can calculate that total H. So a bond enthalpy is defined as the delta H when 1 mole of bonds is broken in a gaseous state. It's always a positive quantity because heat is always absorbed when chemical bonds are broken, and it's always given off when bonds are formed, specifically in a gaseous state. And it increases with the number of bonds between the same 2 atoms. So for example, if I had a single bond versus a double bond, the double bond will have a higher bond enthalpy than the single bond because there's more electrons being shared or exchanged there. Same thing if you have a triple bond compared to a double bond, more energy with the triple bond than the double. In general, a reaction is expected to be endothermic if the bonds in the reactant are stronger than those in the product, and if there are more bonds in the reactant than there are in the products, which means that they have to absorb more energy to be able to break those stronger or more bonds than they would if the products had more. So this explains why some atoms are diatomic, like O2 is diatomic, or H2 is diatomic, all those ones that we've circled on your periodic table. It's because they're more stable and because they require like more energy to be together. They're stronger together. So remember, I think it was in our first lecture, maybe our second, I'm not really sure anymore, but we talked about the first law of thermodynamics briefly when we were talking about James Joule, who was the guy who developed the first law. So that first law of thermodynamics states that in any process, the total energy, the total change in energy of a system, which is delta E, is equal to the sum of heat, which is denoted as Q, and work, which is W, transferred between the systems and surroundings. So then you can get the equation based on that statement, delta E equals Q plus W. This is a very simple equation and will be pretty easy to use as long as you can identify whether or not something is positive or negative. So positive, or Q will be positive when heat is added to the system or work enters the system, and Q and W will be negative if you have heat leaving the system or the system doing work. So we've got another knowledge check here. I'm not going to stop. I'm going to keep going after this one, but I'll explain the answer. So take a moment to figure it out. Pause the video in between. What I want you to do is try and calculate delta E of a gas for a process in which the gas will A, absorb 20 joules of heat and do 12 joules of work by expanding, and B, gives off 30 joules of heat and has 52 joules of work done on it as it contracts. So notice it doesn't really matter what gas we're talking about here. It can be any gas, but you should be able to hopefully know the correct signs of Q and W based on what we just talked about. So take a moment to figure it out, and I'll go over the answers now. All right, so for A, I got 8 joules, and B, I got 22 joules. And that is because you're going to use delta E equals Q plus W. So for A, 20 is positive and 12 is negative, which is what, when you get it, you get 20 minus 12 to give you 8. And B, the 30 is negative and the 52 is positive, giving us the 22. So negative 30 plus 52 equals 22. And that's because absorbing heat is positive, so that's why this 20 joules is positive. And then the system is doing work, which requires like an output of energy, in this case of 12, which is why it's negative. In part B, it's giving off heat, so again, negative 30 because heat is leaving the system. But it has 52 joules of work being done on it, so it contracts, which means that you can add that work into the system, so positive 52. Questions, please let me know. All right, so we're almost done. And I just really want you to think about what does a graph of an endothermic reaction look like and how this compared to a graph of an exothermic reaction. So if you were going to put this information into graphs, what do you think it would look like? What would have more or less energy at the beginning and end of a reaction as time goes on? So again, take a minute to try and sketch it out, and I will show you what some of that is. So here we've got exothermic reactions. You've got the reaction pathway, or basically as time goes on the X, and then the energy on the Y. So if it's exothermic, it is releasing energy to the surroundings, which means that you're going to start with a bunch of energy, but because you're losing energy to the surroundings, your product have less energy than what you started with, so products are below reactants. This picture shows what we call the activation complex. You should be familiar with that from physical science, or catalysts, or reaction rates, all that kind of stuff, where we talked about this hump, this activation energy that's required to get a reaction to go. All reactions have it. So even though you have to input a little bit of energy to break those bonds in the reactants, the products have a lot less energy than the reactants do, so the end is going to be below it, and the change from reactants to products is that delta H. This one shows basically the same thing, but without that activation complex. So again, reactants on top, products on bottom, because they have less energy than what we started with. And endothermic is basically going to be the opposite of that. So our reactants have a lot less energy than our products do because they have to absorb energy from the surroundings. There is still an activation complex, so you have to absorb more than what you end with to make sure that those bonds break and can reform. But that change from reactants to products is the delta H overall. All right, I hope you guys enjoyed this. It wasn't too torturous. I'm sorry my kids interrupted partway through, but that's what life is now, right? So I'll do another lecture probably next week, and I'll get you that quiz for tomorrow. Have a good rest of your week, guys.